Hi guys, Mr. Janowski. This is part 4 of the chapter 13 slides. In the last part, we learned the Stefan-Boltzmann law and how you can combine the Stefan-Boltzmann law with Wien's law and also with the inverse square law and use that to actually figure out the radius of different stars. And beyond that, it turns out stars are classified into two big categories. They're either small, like the sun, in which case we call them dwarfs, or they're big, such as Betelgeuse, in which case we call them giants. So a very binary system. You're either small and you're a dwarf, or you're big and you're a giant. It does get a little more nuanced than that. There are hypergiants, things like that. But basically, two big categories, dwarfs and giants. So, let's get started with the next part. In this part, we're going to learn about a useful way of comparing the brightnesses of stars. So let's get started. So, quick review. What's the law that lets you determine the temperature of a star by observing its light? This is something that we've been doing for chapters and chapters. This is Wien's law. So find the maximum wavelength, plug it into this formula, and that will tell you the temperature of the thing. So from this chapter, what is the formula that relates brightness, luminosity, and distance? That is the inverse square law. So brightness, which is how bright the thing appears to be, is equal to luminosity, which is how bright the thing actually is, independent of who's observing it and where they are, divided by 4 pi distance squared, where distance is your distance from the object you're looking at. So the thing we learned in the last part, what is the law that relates luminosity, radius, and temperature? That's the Stefan-Boltzmann law. So L, luminosity, equals 4 pi r squared, where r is the radius of the star you're looking at, times sigma, sigma being a lowercase Greek s for Stefan, so we use sigma for the Stefan-Boltzmann constant, times the temperature of the star to the fourth. So there's a very strong dependence on temperature. So if the temperature goes up by just a little bit, but that little bit gets raised to the fourth power, that means your luminosity can go up by a lot. So early in this chapter, we learned that we use this satellite, or used to use the satellite called Hipparcos, to measure the distance to some nearby stars, some, more than 100,000 and nearby, within 250 parsecs, and therefore within about 750 light years. So we named this satellite Hipparcos, which is a very clever backronym, basically a made-up acronym for something, to honor this guy, the ancient Greek astronomer Hipparchus. So we're going to learn about something Hipparchus did way back when. So over 2,000 years ago, Hipparchus measured the apparent brightnesses of stars, and he classified them according to the system called the magnitude system. So in Hipparchus' system, the brightest stars he could see, he grouped them together, and he all said those were stars of the first magnitude, or magnitude 1. So that would be stars like Betelgeuse here in Orion, a very, very bright star. So he said, okay, that's a first magnitude star. I'm guessing Rigel is also a first magnitude star. I don't know off the top of my head, but Rigel is very bright as well. So yeah, in this system, the brightest ones, he said, those are magnitude 1. If they were a little less bright, he called them magnitude 2, and so forth, all the way down to magnitude 6. Magnitude 6 stars are the dimmest stars you can see with your naked eye under good conditions. So very bright stars are 1, and the dimmest stars you can see are 6. So if you can find the Little Dipper gives you a useful way of comparing the magnitudes, because the bowl in the Little Dipper is made of these 4 stars, and they happen to be of 4 different magnitudes. So the brightest one in the bowl is a 2, the next brightest one is a 3, and then a 4, and then a 5. So if you want to find the Big Dipper, look for Polaris, the North Star. Polaris, also a second magnitude star, is the handle of, it's the end of the handle of the Big Dipper. So again, this magnitude system, this is apparent magnitude, is another way of saying it. If you say magnitude system, it's implied you're talking about the apparent magnitude system. This is how bright the stars look to us, the observers here on Earth. So this is a very useful system to quickly talk about how bright stars are. Well, stars and other objects. But there's a couple of weird, confusing things about it. First of all, the scale is basically backwards in that the bright stars have the small magnitudes and the dim stars have the large magnitudes. Oh, yeah, that seems a little bit weird. Again, the idea was that Hipparchus said, well, the brightest stars I can see, I'm going to call those magnitude 1. Those are stars of the first magnitude. And as they got dimmer, those became second magnitude, third magnitude. So, yeah, it kind of makes sense if you think of it that way. Another thing that makes it confusing is Hipparchus did this in the 2nd century BC, obviously not using a telescope. He was just doing this by his naked eye. And he tried to put all of his brightest stars in, in the magnitude 1 classification. Turns out some of those stars are actually brighter than others. So now that we can actually measure them and measure their brightnesses very, very precisely, some of the stars that he called magnitude 1 are actually a couple of magnitudes brighter than that, which means a couple of magnitudes lower than that, which means they actually have negative numbers. So a little annoying. This happens a lot in astronomy. Somebody will come up with some kind of system and we'll use the system for a while. And then as time goes on, you have to keep making these weird adjustments to the system and things stop making sense. You'll see. So the magnitude differences, it's all based on the number 100 and the fifth root of 100. So it turns out that a magnitude 1 star, a very bright star, is about 100 times as bright as the dimmest star you can see with your naked eye. So first magnitude is about 100 times brighter than a 6th magnitude. So every difference in between corresponds to a fifth root of 100. And the fifth root of 100 is about 2.512. So if you have a magnitude 1 star, if you're comparing two stars and there's a difference in magnitude of 1 between them, that means the star with the lower magnitude is 2.512 times brighter. So how does a magnitude 2 star compare to a magnitude 3, 4, and 5 star? Well, a 2 compared to a 3, there's a 1 magnitude difference, so it's just the fifth root of 100, 2.512. Excuse me. If you're comparing a 2 to a magnitude 4, there's a 2 magnitude difference. So you don't just double 2.512, you actually multiply 2.512 times 2.512, and that gives you 6.31. So if the stars are 2 magnitudes different, the lower magnitude star is 6.31 times brighter. And if they're 3 magnitudes different, you're not just tripling 2.512, you're raising 2.512 to the third power. So 2.512 cubed, and that's 15.9 times brighter. So if you were comparing Venus when it's at its brightest to the bright star Aldebaran, how do their brightnesses compare? Well, Venus, clearly not a star, but you can use the magnitude system to describe any object, the planets, moons, things like that, comets as well, when there are bright ones of those around. So Venus at its brightest has an apparent magnitude of minus 4.2. So it's way brighter than even a magnitude 1 star. So the bright star Aldebaran is a magnitude 0.8. So that is still a very bright star. How do their brightnesses compare? So what you do is you take their magnitudes, you find the difference, and the difference between 0.8 and negative 4.2 is 5, and then you plug it into this idea. So a 5 magnitude difference means a brightness ratio of the fifth root of 100 raised to the fifth power, which is 100. So that's telling you that Venus is actually 100 times brighter than Aldebaran. So just to be extra confusing, when you say magnitude, it is implied that you're talking about the apparent magnitude, which is how bright the star looks to an observer on Earth. So yeah, that is related to the earlier idea in this chapter, brightness. It's how bright it looks to you based on where you're observing it from. The confusing thing is we also sometimes refer to the absolute magnitude of a star, which is related to the star's luminosity, which is how bright the star actually is. It's independent of its distance and its distance from us, the observers on Earth. So how does absolute magnitude work? We picked some nice round number. We went with 10 parsecs, and we said, if you were to take that star however far away it is, however far away it actually is, and you could just move it to 10 parsecs away, how bright would it actually look? What would its magnitude be? So here we're looking at, this is what the constellation Canis Major, the big dog, actually looks like from Earth, and Sirius is the brightest star in this constellation. I think Sirius is actually the brightest star, period. The highest the highest apparent magnitude of any star, because it happens to be fairly luminous and fairly nearby. So yeah, if you were to look at Sirius at night, it would look like this, the picture on the left. If you look at Canis Major, it would look like this, and Sirius would be the brightest star. But again, remember, these stars are all different distances away. So the idea of absolute magnitude is if you could move the stars so that they were all the same distance away, so that all of the stars were 10 parsecs away, about 32.6 light years away, how bright would they seem? This constellation would look like this. So stars that weren't that bright before, particularly this guy, so kind of in the belly of the dog, it looks like, um, fairly low apparent magnitude. But if you were to move it to 10 parsecs away, it would look a lot brighter. So that means the star actually is much further than 10 parsecs away. So yeah, all the brightnesses change. So, quick review. What is the name of Hipparchus' system for comparing the brightnesses of stars? This is called the magnitude system. Now, according to the magnitude system, if Venus is 5 magnitudes lower than Aldebaran, how do their brightnesses compare? So again, you find the difference of their magnitudes. It ends up being 5 magnitudes. And the magnitude system is based on the fifth root of 100. So if they're 5 magnitudes different, you take the fifth root of 100, you raise it to the fifth power, and that gets you back to 100, which tells you that Venus must be 100 times brighter than Aldebaran. So that's it. Hopefully that's helpful.